So hello to everyone. My name is Yaroslav Nikulin, same as Yaroslav. I'm head of AI at Therapixel, French company creating AI for medical images, more precisely for mammographies, 2D and 3D. By the way, that's kind of exceptional case, I would say, which does not suffer from what previous speaker explained about the difficulties of creating medical AI. And my today's presentation would be about multimodal transformers as a potential disruptive technology for radiology AI. So let's go, let us unpack this. First of all, you all probably heard about disruptive technologies without maybe asking what this is exactly. And actually, there is a formal definition and there is a framework around this notion developed in this book, The Innovator's Dilemma, which, by the way, I highly recommend. After that, you will never see the development of technologies as before. So, disruptive technology is something which is usually opposed to sustaining technology. Sustaining technology is something which is improving existing products along known and basically same metrics. We can think about, for example, CPUs. We just want them to run faster, to consume less energy, etc., etc. We can think about petrol cars engines. We want them to be basically more powerful, consume less fuel, etc., etc. But disruptive technology is something different. It's usually based on already existing methods. Actually, it can be even simpler than sustaining technologies. But first of all, it invents a new value proposition, appealing first to a niche or a new market, which economists usually call down market. Second, it improves at a faster pace than established tech, or at least it catches up quickly with mainstream market demands. And third, it invades upmarket and kills all the products. I guess you can notice this economical flavor of this definition. We are speaking about technologies, but the author comes from the business world, and basically disruptive technology needs to gain market in a sense. So it's not enough just to create a new invention. What is even more tricky is that established customers usually say at first that they are not interested in disruptive technology at first until it competes with existing products in main metrics and also offers additional advantages. Here, this is an illustration of a sustaining technology. Basically, we start to work on something new to improve existing metrics. At first, it works not that well. Then progressively it improves. Then it's ready to replace the existing approach in a product, and then basically that's how it develops. But disruptive technology is something which again invents a new value proposition, improves faster. It starts from usually least demanding customers, down market, then it catches up quickly with what main market wants in terms of performance, in terms of some key metrics, and then basically it kills all the products. Okay, let us consider a couple of examples. First example, solid state drive versus hard disk drive. New value proposition, SSD are faster, smaller, but initially they had less capacity and limited write endurance. They attacked niche markets first. Small devices, military, high-performance laptops. They improved at a faster pace, and SSD capacity and endurance caught up with hard disk drives around maybe 2018, 2020. And basically now, well, you can see it all. It invaded mainstream markets, and now SSD is standard for laptops, for example. And hard disk drives are mainly used for archival backups in clouds where you don't need basically just a fast access, and it's a little bit less expensive. Second example, by which I would like to illustrate that disruptive technology is not equal to invention. For example, it was not the first car which was a disruptive technology with respect to horses. It was actually Ford's conveyor, which opened mass market. In the same way, the first electric car with respect to petrol engines was not disruptive. And actually, I was astonished to discover that the first electric vehicle was created, and you can see here this nice picture. It was created in the end of 19th century. Impressive. But again, that was not a disruptive technology, since it was only first mass production, Tesla, which basically started to gain first niche market and then main market. So yeah, new value proposition, you have fewer moving parts, you don't have any noise or emissions, good for cities. Probably you have better driving experience, subjective, but most importantly, it's very different from legacy cars. You don't have transmission, for example. at-home refueling, but at first they had short range and long charge times in the beginning. They improved fast, and now electrical vehicles are as long range as legacy cars, and basically they cost at least comparably. What is interesting here is that contrary to, most cases, Tesla started not from down market, which is usually less expensive and simpler products, but from up market. Supercars, expensive cars, Tesla Roadster, their first model. Okay, this being said, I would like to shortly present the current state of industry in radiology AI. What we have right now, we have many narrow AI products. Some of them can even have superhuman performance, as our product at Therapixel, which is called MammoScreen, which is basically analyzing mammographies and basically predicting several things. Behind this, we have several narrow AI models trained to solve a very specific task. For example, detect malignant lesions in mammography, predict breast density, maybe check a list of image quality criteria. For another modality, for another X-ray images, like from emergency rooms, we can think about detecting fractures, predicting bone density, etc., etc. The point is, all these models, they're very narrow, and they predict a very fixed objective. Yeah, here, by the way, you can see how we merge the predictions of all these narrow models into one single nice user interface. So we are pre-filling some things, like breast density, quality, whether it satisfies criteria, etc. Here you can see another example. That would be from our partner company called MilView. And here you can see the detection of a fracture, elbow joint effusion. You may also want to predict pneumothorax in X-ray images of a thorax. Again, point here is that many narrow AI models. What it also means that there is a complex orchestration of many models to then fuse their prediction into a nice graphic user interface. It certainly can be done, and it's already done for some modalities, like we did for mammographies, MilView did for X-ray images, but it's not scalable to a more holistic solution. Another problem, I would say, created by that is rising of AI platforms. Basically, in order to simplify life of IT departments of hospitals, AI platforms, well, you can see them as like Play Market for Android applications, and this is just a unified interface for hospitals IT department so that they can, instead of speaking to like dozens of AI vendors, they can speak just with the platform. But of course, they want their share, and I feel like it's not that efficient. Okay. So, in my opinion, it's my like hypothesis and reflection during maybe last 2 years, is that AI in radiology is lagging behind what we can call general AI domain. Here I suggested basically name AI 1.0 and AI 2.0. So how can we characterize AI 1.0? And by the way, that's where all current narrow AI is allocated. We have specific data sets with fixed labels. Basically, we precisely encode that, for example, 0 label is benign, 1 is suspicious, 2 is malignant, etc., etc. Narrow tasks, so no flexibility. We can't do zero-shot classification detection. It's monomodality, for example, only on images. And also, models are usually based on convolutional neural networks. There is no problem with CNNs. They're great, simple, they work well. But they are too image-focused, and they cannot be efficiently scaled. Let me put it this way. AI 2.0, well, examples, you know them. They use very diverse, sometimes internet-scale data sets. I mentioned here ChatGPT, of course, other visual language models, Glip, that's just 2 famous papers I highly recommend. They solve, in a sense, more general tasks. For example, Glip can do zero-shot image classification. What it means? It means that instead of predefined labels, you can come up with a new data set. You say, I want you to classify them into these categories, and you give them in the form of free text, and it's capable to do so. Same idea for zero-shot detection. You have your data, you take your model, and you say that, okay, I want to detect this, and that. And you really can put rich descriptions with adjectives, everything you want. There are usually multimodal, for example, at least images plus text. And all the flexibility I'm talking about comes from this general form of signal as text and not as encoded labels. Models are usually transformer-based, and they're usually much, much bigger, since transformers really start to shine when we need to scale and connect different modalities. Okay, now the key question, basically, can we expect a ChatGPT moment soon for AI in radiology? Maybe you have heard about that a lot of narrow text AI were disrupted by several consecutive ChatGPT releases. I can name chat with your docs wrappers like chat PDF, write for me wrappers like Jasper, maybe you have heard about, chat search wrappers, that would be like Perplexity, basically improving search in the internet, or domain-specific assistants such as an assistant for laws, an assistant in finance, etc., etc. All of them basically died because now, for example, you can take ChatGPT, upload a PDF, and you don't need Chat PDF anymore. Why bother? And it's also smarter. Media called this thin wrapper problem. Basically, what is the added value if your product is just a wrapper around OpenAI or another big model? But I believe that even if they had their proprietary data set and their own models, that would have changed strictly nothing, since if the final product is not better according to some real-life metrics, not just some lab scores, why bother with narrow solution when you can have just your ChatGPT or Mistral AI or Llama model? So an analogy and the hypothesis is that, can we say that LLM wrap kind of medical AI platforms, they are both useless middlemen? Can we also hypothesize that narrow NLP models like narrow radiology AI solutions, and if only we could create a more general AI, they would be no more? Okay, so having thought first of all about this, I started to push for a new research access. Basically, can we at least de-risk and understand whether multimodal transformers can replace our own several narrow AI models? Yes, they are for one single modality, but we still have many of them. To do so, we selected first just 4 specific problems and thus 4 associated metrics to benchmark against our own narrow AI models. First problem, implant presence. This white blob here is basically breast implants. This is a very easy binary classification problem. Since it's evident, achieving 99% of area under a curve is very doable. Breast density, second problem, that would be 4 classes classification problem. Breast density can go from A to B to C to D. Here you can see an example of breast density A, basically almost transparent organ. And here you can see an example of something closer to D, basically highly opaque, non-transparent tissue. And it's also much more difficult to find malignant lesions inside such dense images. Something like 75% of accuracy is very doable. Again, here we encounter the same issue. Radiologists don't even agree with themselves. Well, that's life, but that's what we can get. Malignancy status, this is the most difficult of all problems. It's not enough just to basically find the lesion inside an image, because those can be benign, and it's a very fine texture recognition problem. So that's why basically you can solve it well, but you really need to try hard, to perform a lot of experiments. That's what we did. And something like 91% of area under a curve is achievable at the image level. And if you add some tricks, you can actually get superhuman performance, which we demonstrated in our latest clinical study. Some tricks, it's like model ensembling, proper post-processing and pre-processing. I will not speak about this now. I just want you to concentrate on some fundamental values which make sense. Yes, and last, malignancy localization, almost the same, but instead of predicting the status of the overall image, you really need to localize the problem. We are using a slightly different metric for that, localized ROC, and we can achieve around 87% at image level. And again, plus some tricks, you can get superhuman performance, again, on this particular task. So yes, we started to do that. here I would like to very quickly present the overall architecture of such a multimodal transformer. So here we have an input image in high resolution. We are still using in only this part a convolutional neural network, pre-trained and frozen, just to extract image features. Then that would be a deformable transformer encoder, and here we will have the deformable transformer decoder. Here we will have learnable vectors of object queries and what we call visual queries. We will push object queries through decoder. It will interact with features extracted from the input image. Then it will be decoded by detection head into detection loss. And the most interesting part here is how we define ground truth. You remember this problem that AI 1.0 we had fixed specific labels. Here we are replacing those labels, but by embedding of the text which describes what this is exactly. So here, for example, that would be for malignant distortion describing this part here. Again, that's going to be free text, push it through text encoder. Here we're actually using a BERT model, and then we will just align text and image representation via image text contrastive loss. And same will happen to visual queries which do not have localization, such as breast density, they don't have localization, and they will be mapped against whatever description you may want to put for those images. Yep. If you are interested in methods that we were using, here I put basically the name of some models. We have recombined and recompiled and adjusted some ideas and methods from deformable Detor, Clip paper, Blip2 paper, and Glip. So all of those are public knowledge. If you want, you can have a read, but you really need to understand the prior state of the art in order to use them efficiently. Okay, so where we are at Therapixel after 1 year of R&D efforts about working on exactly that. Yes, so here I put the 4 problems we selected with 4 associated metrics, and we compare narrow AI model and multimodal transformer. What is interesting here is that I created the first version of this table maybe 2 months ago, and since then I had to update it maybe 3 times. Before, multimodal transformer was like lagging behind several %, but that was already something interesting, like proving the point. But since then, we had a couple of nice breakthroughs, and we basically closed the gap on most of them. So for example, we do understand how to close this little gap. We just need to play a little bit with sampling, since implants, they're a little bit rare, and machine learning practitioners, you certainly know that it's difficult to work with rare classes. Same here, little gap is breast density. Most importantly, we basically caught up in performance with narrow AI models for malignancy tasks, and even surpassed on malignancy ROC. Yeah, here I am not entering into too many details, since, for example, those statistics, you should look into other different metrics in order to understand that everything is fine. You also need to stratify data according to device used to acquire images, patient age, ethnicity, etc., etc. So all of it should be analyzed in much more details, and that's what we are basically doing. Still, those global aggregated metrics make sense, and the main message here is that we finally persuaded ourselves that yes, such a model, basically one model to rule them all, at least on our data on this particular modality, yes, it can be done. And also, more we work with neural networks, more we agree with a principle which I can call data main limit. Provided that you fix all bottlenecks and inefficiencies in your model's architecture, provided that you know how to train your model efficiently, the quality of your solution will mostly be limited by data and problem itself. That's what we have rediscovered here. I first discovered this principle when people who were training generative models, they first used GAN, generative adversarial networks, then they passed to stable diffusion models, and I read this opinion that basically, if you do everything right, you will be most limited by your data set. And our conclusion, again, was that properly adjusted transformers provide a functional space well suited to match the performance of all narrow models. Sounds great, isn't it? Very promising, indeed. However, I would like to comment and mention some obstacles for this potential ChatGPT moment in radiology, and I will mostly repeat some of theses of the previous speaker. First of all, data, of course. LLMs could benefit from internet scale data, and getting medical data is much, much more difficult. It's doable, and there is data. It's just well protected for good reasons, and we can't easily get a lot of it. Second is heavy regulation of anything healthcare related. So yes, we can probably create a big, beautiful model doing everything, but then you will have to validate it per use case, actually. Second, for such a model to realistically tackle something like this, you will need big investments. I would say that to be serious, you really need tens of millions, since one single machine, for example, with 8 latest GPUs by NVIDIA will cost you at least 300K, and just one machine, you will need several of them. You will also need highly performant data storage. You will need highly qualified AI scientists who understand what they are doing instead of just running, basically crushing noise on GPUs. And again, you will also need some data. Some data sets are publicly available, and yes, we can gather a lot of data for some modalities, but definitely not enough. And highly likely you'll have to buy some data. This is also a market exists. Last point is about market adoption. It's already painful to push for the adoption of already existing and well-performing, most of all, models. And if all big modalities are covered by narrow AI solution, basically why hospitals would bother about like breaking everything again and putting in place new pipelines. My hypothesis is that as any potential disruptive technology, it could start in a niche market. What we address right now with our solution is actually top-notch hospitals in the US and in Europe. But can we think about small clinics in remote and poor areas, where basically having a general model, which certainly will underperform at first with respect to narrow models, but it's much better than do not have any radiologist at all. Finally, it's very easy when you start something like this. Very easy to be several years too early when trying to create such a fusion of narrow AIs. But stakes are high. Such a model which could approach AI radiologist, basically a very general model which is capable of analyzing any kind of images you like, it will target market of size of at least tens of billions, certainly. Plus potential to become something much, much more interesting, not just reproducing the functionality of narrow AI models, but also basically doing cross-analysis, taking into account other data of the patient, and in future potentially replacing a full consortium of specialists, since that's exactly what's going on with difficult cases when there are, for example, several diseases or problems, and they really gather a consortium of specialists specializing each one in one organ or in one subsystem of your organism, and then they decide what would be the best solution. Yep, that's about it. Instead of conclusion, I would like just to say that technologies live really their own life. Highly unpredictable and non-linear one, I would say. They advance step by step, since at each moment you can only do what is like immediately possible and available. But a chain of such steps can lead you very far. Analogies are good, and I tried to leverage some of them, but real world is incredibly complex. No one has the full picture. So, yeah, I was happy to share with you this my reflection and our current results. Thank you for your attention.